So this is a very interesting problem about strings. So this problem is often referred to as a string break problem, or some books and articles also call this as a word break problem. So let's understand what this problem is all about. I have an example here, right? So what we are given here is very important, right? So we are given a string S like this, applied course, and we are given a dictionary. This D is a dictionary. What is a dictionary? A dictionary is nothing but a hash table. Okay, dictionary is a special name that is given to hash. So dictionary and hash table mean the same thing, right? Which means I can search for any string in this in order of one time. So order of one time search is possible, right? So this is a dictionary or a hash table. Again, if you know Python, in Python, hash tables are called as dictionaries, right? So dictionary or hash table mean the same thing. So if I give any word and if I want to search if that word is present here, I can quickly search in just order of one time, right? So I'm given this sentence and I'm given this dictionary D, which consists of multiple words. Now the question we want to answer is this: can I construct, or can we construct the sentence S using words in D? For example, can I construct applied course using only words that are there here? Yes, I can take applied, I can concatenate with course, and the only operations while I'm constructing, the only operations that are allowed are concatenation. Concatenation is the only operation that is allowed. So suppose if I take the second word here, which is applied, because there is no concept of first and second in a hash table, right? Suppose if I take this word applied, which is present here, and if I concatenate with course, I would get applied course, which means this sentence can be constructed, or this word S, or the sentence S can be constructed using the words that you have in this dictionary D. So the answer, this is the question that we want to answer. Is it yes or no? Right? This is the problem. We should always answer yes if this string or word S can be constructed using words in my dictionary D. Again, here I'm given that the time to search in this dictionary itself is order of 1. So I can search for any string or any word in this in just order of 1 time. Right? So let's look at some more examples. So this is the case where the answer is yes. So this is a case where the answer is yes. Let's take another example. Let's take this example here, right? So I have my string S as applied course is good. No spaces, okay? So there are no spaces here. And my dictionary D consists of the word course, word applied, word good. Now if you notice, I can concatenate applied course, but I don't have ease anywhere. So in this case, the answer is no, because I can't construct string S using the words in my dictionary D. Just wanted to give that example very importantly, right? Now let's look at another example. Okay. This is a slightly tricky example because look at this. My word S is hello world, a very common example in whole of computer science, especially in programming. And my dictionary consists of H, again, this word consists of only one character H, but this is a word, or this is a string if you want to think about it. Words or strings mean the same thing, right? See, here also you have a string HE. Here you have a string E. Here you have a string LLO. Here you have a string WORLD. Now to solve this problem, how do we solve this? So let's assume I start with hello world, right? So let's assume my string that I have is hello world. One strategy that I can employ, because remember that this is a hash table. This is a hash table, which means I can search very quickly. So I'll start from the left side. One strategy that we can employ is we'll start from the left side. I'll just take just the first character here, H. I'll search in this. Right? Is H present in this dictionary? I can search it in order of one time. Yes, H is present, right? H is present. So now I am yet to find. Now look at this. This is a whole word, right? This is a whole word. What is the length of this word? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 characters in this word from 0 to 9, right? My problem has from 0 to 9. Okay, this is what my string indices are. This is index 0, this is index 9. The first index 0 itself, I have found it, which means I have a problem of size 10 here, which consists of 10 characters. H is found. Now I have to just search for this. Now I have to just search for ELLO world. If I find this, my problem is solved. Right? That's one possibility. Now here again, I'll start searching. What is the first character here? E. I'll search if E is present. Yes, E is present here. Okay, so E is present. Now what am I left with? LLOWORLD. Now I'll search for first character L. L is not present. Then I'll search for two characters, two L's. Are two L's present? No, two L's are also not present. Then I'll search for three L's. Yes, LLO, sorry, not three L's, LLO. Yes, LLO is present in the dictionary. So what do? So LLO is present. So now I have to find for world. Now I'll search for world. I'll search for W first. W is not found. I'll search for WO, so on and so forth, till the time I search for the whole world. I search for the whole word world, right? When I search for it, I get it. So now if you think about it, this is sort of like recursion, right? If you think about it, this is sort of like recursion. Okay, that's a hint that should be obvious here, right? Because you're taking a problem of size 10, right? You're searching for the first character, first two characters, first three characters, so on and so forth. Whenever you find it, you're now getting a smaller problem here. In this case, you got a problem of size 9. In this case, you got a problem of size 8. In this case, you got a problem of size 5. So you're reducing the problem size by recursively solving the problem, right? I have a problem of size 10 that I'm solving here. I found H. Now I'm solving a problem of size 9, right? So if you think about it, recursion is clearly evident here, very clearly evident here, right? Now the next question I have here is, so recursion, very good. Now the immediate question, okay, we can solve this using recursion, but we know recursion plus overlapping subproblems implies dynamic programming. So are there overlapping subproblems also here? If they are there, we can use the whole machinery of dynamic programming, right? The first thing, whenever you have a recursive problem, it makes very logical sense to search for overlapping subproblems, right? So now are there overlapping subproblems here? Let's see. Look at this. Again, this is only one path that we have followed. There is another path also that we can follow here. The other path here is, after I've searched for H, probably this may not work sometimes, right? I also have to search for HE. Okay, is HE present? Yes, HE is present. The moment you notice HE, I now have to solve the problem of world, right? Probably, for example, imagine E was not here. Imagine E was not here. Then you would break this problem into this problem, but this problem cannot be further broken down if E wasn't there. Remember, if E wasn't there, we would get stuck here, and then we would say, I can't solve this problem anyway, so I'm done. Then I have to track back. That's how recursion works, right? I try to solve a subproblem, I couldn't solve it, then I'll go and try HE, right? So if you notice, I can draw a recursion tree like this, wherein in the first case I found H. Look at this, I found H, that's why I've gone down this path. But I've also found HE. So I might also go down this path, because I don't know which path leads me to the solution in my recursion. See, this is my recursion tree, right? I don't know which path leads me to the solution. Because if any one path leads me to a solution, if any one path leads me to an S, my answer is yes. If all the paths lead me to a no, so any one S, if all no, then my answer is no. If any one path leads to a yes, I will answer yes. If all of them lead to no, only then I'll say no. Right? Very simple question here. So now if you notice, if I draw my recursion tree like this, with H I get ELLO world, then with E I get LLO world, but I might also want to go down this path. Right? If you draw the whole tree, HEL also I'll search, but I don't find HEL. So that path will return back. HELL, I don't find anything there, so on and so forth. Now, if you notice this recursion tree, there is overlapping subproblem, because this subproblem and this subproblem are the same. So the tree that you will encounter here, the recursion tree and the recursion tree that you will encounter here are the same, right? Because the subproblems, look at this. This is your standard recursion tree, and you're seeing the same subproblems being solved multiple times, which means now you have recursion, your overlapping subproblem. So the whole problem is dynamic programming. But before we write the dynamic programming itself, in this case, this is slightly tricky. So let's actually write the programming logic step by step. I've written the whole programming logic. I'll explain this step by step. The reason I've written it prior is because I wanted to use all these colors, the white color, the red color, the green color, so that it's easier for you to understand. Okay, so let me break this down and explain it piece by piece. Okay, so let's assume I have a recursive program like this. My recursive program is string break hello world. Then how do I answer this question? I say, if the dictionary contains, so d dot contains basically means, does the dictionary contain the string hello world? If it contains, I'm done. Or, look at this, this is logical or. Okay, if the dictionary contains hello world, I'm done. Problem is solved. Or if the dictionary, if the dictionary or the other word, the second option here is I'll solve the subproblem with just the first word. Look at this. This is one way of writing the programming logic, right? Again, this is equivalent to writing the recursive formula. This is equivalent to writing the recursive formula. So what we are writing here is the recursive formula, literally, with the example, so that it's easier for you to understand. Because we have seen that recursion occurs, but we have not written the recursive formulation itself. So that's what I'm writing down here. So if D contains hello world, this is like a boundary case, right? This is like a boundary case. This is like a boundary case, problem solved. Or if string, there is another boundary case, which is if the string itself, if the length of the string is 0. If the length of the string is 0, that's also a boundary case, right? So in this case, the length of the string is not equals to 0. So string break of hello world is if the dictionary contains hello world, or we solve the subproblem with only the first character here. So we have our hello world here, right? We have your hello world here. So we recursively call, look at this, we are recursively calling the same function string break with just the first character. For the rest of them, if I now find it in my dictionary, I'm recursively calling this. If this returns true, and this is logical and if the dictionary contains hello world, if both of these are true, then I have a solution for string break hello world. See, this will be true if this is true and this is true. Or I can recursively call my string break with the first two characters. And now if the dictionary contains the rest of the characters. Look at this. If this is true, or this is true, or this is true, or this is true, so on and so forth. What will be the last case? The last case will contain all of these except the last one, except the last character here. So recursively, look at this. How many to solve this problem, I'm calling a recursion here. I'm calling a recursion here. I'm calling one more recursion. Or, see, these ORs will always be there, right? String break on everything except the last character. And if the dictionary contains the last character, right? This is your recursive formulation. Again, in this case, I wanted to show you the recursive formulation with an example so that you easily understand it. And the most important thing, the very important thing here is, this is logical OR, which means if this is true or this is true, if any of them is true, right? I'll simply shortcut. If any one of them is true, I can return true. I don't have to evaluate the others which are below that, right? With this logic, now let's go and think about it from a dynamic programming perspective. Again, when you're given a dynamic programming, when we know it can be solved using dynamic programming, we always prefer bottom-up dynamic programming, right? So let's construct the bottom-up dynamic programming as follows. I'll construct the bottom-up dynamic programming in such a way, that I'll use a table called DP. Okay, this table is of length 0 to n, where n is the length of your string, See, your S itself has indices from 0 to n minus 1. Your S itself has indices from 0 to n minus 1. But we're creating one more index here. This array length is n plus 1, because there is also 0, there is also n. Now, this value will be equal to true. Look at this. This value is equal to true, right? So this value. So dp of I, let me write this down. dp of I equals to true if S 0 to I minus 1. If 0 to I minus 1 can be constructed using, if it can be constructed using my dictionary D. It is false otherwise. Okay, this is how I'm defining this. It is false otherwise. Okay, this is my table. So look at this. There is overlapping subproblem, right? So I can always memorize, or I can use memoization. I'm sorry. I can store things in a table, or I can use memoization. Here, this is my memoization table. That's what it is, right? So what am I saying here? What is my final answer? If this value is true, what does that mean? If this value is true, that means string from 0 to n minus 1 can be constructed using D. And that's what we want to find out, right? So we'll start filling this. Again, what about 0? What will this value be? This value by default will be true. Because what does this mean? This means string from, look at this, 0 to minus 1. Makes no sense, right? So this value will fill it by default with true. Rest all the values will fill using this recursion concept. Now, instead of writing this recursion using the function SB or string break, if I have to write it using my DP array, right? This is my memoization array, right? How do I write it? Very similar logic. DP of I is what? What is DP of I? DP of I basically means string from 0 to I minus 1 can be constructed using my dictionary D. When will this be true? This, I can construct my string from 0 to I minus 1 using my dictionary D, or this will be equal to true only when DP 0 equals to 2. Look at this. DP 0 equals to 2 and DP 0 is by default true, always true, right? That's what I said. And D contains this whole string. What is this? What is this first line equivalent to? This first line is equivalent to this case. D contains the whole string, right? It's equivalent to this case, right? D contains the whole string. See, this is anyway default true. What does this mean? This means D contains the whole string, right? Or what is the second case? DP1. DP1 basically means, look at this. This is 1. DP1 basically means the string break H with just the first character returned true to me, right? If this is true and if D contains string 1 to I minus 1. What is this? This is string 1 to I n minus 1. In this case, right? Look at this. Exactly the same logic. I'm replacing your SBs with DPs. I'm replacing this D contains whatever string is here. I'm just keeping it as is. D contains, I'm just changing the indices. Look at this. If you think about this, to compute DPI, I need J from 0 to I. Look at this. To compute DP, this is very important, right? To compute DPI, I need J's from 0 to I itself, right? And this is the logic. And this logic will help us construct the program for it very, very simply, right? So let's see the program. It's actually very simple. It's literally 6 lines of code, or if you write it in pseudocode. DP0 is true. Here I'm creating an array DP from 0 to n, right? This space complexity here is order of n space, right? Now what am I doing here? For I equals to 1 to n, see, I'll keep using this formula here to keep filling DPIs, but I'll fill from I equals to 1 to n. For I equals to 1 to n, for j equals to 0 to I. Why is j equals to 0 to I? Because of this logic. Because I have to compute all these logical ORs, right? I have to compute all these logical ORs. That's why I'm keeping j equals to 0 to I. By the end of this loop, look at this. This loop basically computes DPI for me. This loop, this yellow colored loop, right, computes DPI for me. To compute DPI, I need j. Look at this. I need j from 0 to I. And what is the logic here? If DPI and D contains Sj I minus 1. That's what it is, right? Look at this. Look at what is this? This is DPJ and D contains j to I minus 1. See, each of these conditions, this condition is what is being computed here. This condition, again, since it's in a loop, I have this condition followed by this condition. So for this thing, I'm writing this, I'm using the loop variable j to loop through this, followed by this, etc. Right? So that's what is happening here. Di equals to true. If this is true, look at this. If any one of them is true, DPI will be true. And I don't have to compute the others below that. Right? So that's what I'm doing here. If this is true, then Di equals to true. Or DPI, sorry, I should call it DPI. Let me call it as DPI equals to true. And I break. Why am I breaking here? Very importantly, because if I know that this is true, let's assume this is true. This whole line is true. Then what is the point in computing the rest of them? I don't need to compute it. Right? So the space complexity here is order of n. What about the time complexity? Look at the time complexity here. This is just simply 2 loops. For loop from I to n, j loop from 0 to I. Very simple loops here if you notice. The time complexity here is order of n square. That's all. You have a polynomial time algorithm or an order of n square algorithm with order of n space. Very simple problem here. Again, the crux of the idea, again, this problem is very, very straightforward because one good aspect about this problem is to come up with examples like this, where you have things like H, HE, E, because only when you come up with examples like this for this problem, you'll be able to recognize recursion and also overlapping subproblems, right? So coming up with examples is an important part of this, of solving this problem. Now, once you come up with recursion and overlapping subproblem, there is a challenge here because writing the recursive formulation is not straightforward, because the recursive formulation involves logical ORs and logical ANDs. So that's why I've not written it in the typical mathematical formulation that I typically write in, right? I've written it like this, right? That's why I've taken an example, because it becomes easier for me to write the programming recursive formulation. And then once I get this recursive formulation, obtaining this dynamic programming based formulation is straightforward, right? And then coming up with the bottom-up solution with memoization tables, that's all straightforward, right? So the only two important aspects here is the trickiness in constructing the recursive formula. This is one of the tricky aspects. The other tricky aspect is to come up with good examples to recognize recursion and overlapping subproblem here. That's all.